Good afternoon, everyone, and welcome to our panel discussion on tackling the Texas energy crisis. I'm Dr. Jen DeRosa, the Program Coordinator for Energy Policy and Climate Program here at Johns Hopkins University. Now, for the past 12 months, our homes have become our safe havens. They've become our retreats as the pandemic wages outside. Yet in mid-February, a series of severe winter storms turned the homes in Texas into a cold confinement the moment the electricity clicked off, and residents felt the warmth seep away. I reached out to a number of members of our Hopkins community before hosting this event, and I spoke to people in Houston, Austin, Texas, and Dallas that were affected by these substantial power outages. Some people stayed in their homes, going 90 hours without power. Others contacted neighbors, friends, relatives, and really anyone with power in order to take their children so that their children had a warm place to sleep for several days. Some people slept in their homes but spent most of their days driving around in their car in order to stay warm. Food from the freezer was taken outside and placed in the snow, and snow was brought inside and melted and then boiled to make drinkable water because the power outages affected water treatment plants and groundwater pumping. For many people, water pipes burst and damaged their homes, and some of the most vulnerable people passed away from hypothermia in their own homes. The events that occurred in Texas in the second half of February are heartbreaking, and people are still dealing with the repercussions of this tragedy as we speak today. Electricity is what makes our homes the ideal retreat in modern times, especially modern times of strife, like during this pandemic. You're comfortable right now listening to me talk, yes? In your heated home or your cooled space. You can watch movies on demand. You can work remotely for 12 months. You can cook anything you wish in your kitchen. That's all thanks to electricity. But our talk today is not on the marvels of electricity. Rather, we're going to take a closer look at the electricity in Texas and how it reaches the homes of Texans. And in addition to that, what kept the electricity from getting to so many homes of Texans in the second half of February. So here with me today are two of my colleagues from the Energy Policy and Climate Program at Johns Hopkins University, Dr. Jeremy Lin and Professor Alex Gilbert. Jeremy Lin has over 20 years of experience in the power industry and power markets in the US, including 12 years at PJM, which is the largest electricity market operator in the US. He has extensive experience in the design, planning, and operation of wholesale electricity markets, as well as power system operation, planning, and reliability. And Jeremy also published a book called Electricity Markets, Theories and Applications, and he currently works as a freelance consultant. And Alex Gilbert is also here with me today. He's a complex systems researcher who focuses on governance and market design for energy, nuclear, and space technologies. He's a project manager at Nuclear Innovation Alliance, where he advances regulatory and policy reform for advanced reactors to support climate mitigation. He has worked in the private sector as an energy market analyst and climate policy consultant. And Alex's academic work explores the intersection between energy markets and climate governance. So Jeremy, as we get started, before we discuss the events associated with February winter storms, can you explain how the Texas electric power grid and the energy market system is different than the Eastern and Western power grids of the US?
Good afternoon, everyone. Enjoying the nice weather now. I'm Jeremy Lin. I'd like to thank Jen and Dan for organizing this panel, which is very timely and relevant. I also like to thank Jen again for inviting me to this panel and nice introduction. To answer Jen's question, let's start with the power grid structure in North America, particularly the United States. As you might know already, the power grid in the US is divided into three major interconnections. The first interconnection is called the Eastern Interconnection, which covers the grid area on the eastern part of the country. The second interconnection is called the Western Interconnection, which covers the grid area on the western part of the country. The third interconnection is called the Texas Power Grid, or more correctly, the ERCOT, which stands for Electric Reliability Council of Texas. ERCOT was formed back in 1970, pushed by the federal regulations to ensure the reliability of the national power grid. 5 years later, the Texas state legislature created the Public Utility Commission, which has an oversight of all electric utilities in Texas, and by extension, an oversight on ERCOT as well. In 1996, ERCOT became the first independent system operator, aka ISO, in response to the growing calls for forming a competitive electricity market, also known as electric system restructuring. And that's happening all over the country. ERCOT does not cover the entire state of Texas. It only covers about 90% of the state of Texas. For example, the electric utility in El Paso, called the El Paso Electric, is now part of the ERCOT. El Paso Electric has connection with the Western grid in New Mexico. So the number of customers under ERCOT power grid is about 26 million, even though the total population in the state of Texas is about 29.5 million. Similar to other ISOs or RTOs, where RTO stands for Regional Transmission Organization, ERCOT has three major responsibilities. The first one is to operate the power grid reliably. The second is to conduct system planning or grid planning. And the third is to run a competitive electricity market. I'll get back to this market operation a little later. The power grid in Texas, in this case ERCOT, has two asynchronous ties with the Eastern Interconnection. Asynchronous interconnection means the DC or the direct current interconnection, in contrast to the AC interconnection. The capacity of these two DC ties is about 2,000 megawatts. The advantage of the DC tie is that you have control over whether you allow the power flow and how much power flow you want at any given time. So in terms of system operation, ERCOT responsibility is to maintain the reliable power supply to meet the load demand on 24/7 basis. ERCOT is also responsible for planning for transmission system upgrades and planning to keep up with the growing load, growing generation, and other changes in the system. So back to the market operation, ERCOT also runs a competitive electricity market within its own operating territory. Transmission and distribution businesses are regulated, but the generation sector is open for competition. So if you're a generator owner, you compete in the ERCOT energy market for the right to produce your energy under the order and guidance of ERCOT and the right to earn revenue. Generators need to earn revenue to survive in the market environment. With regard to the differences in markets, ERCOT markets has energy market only, so we call it energy only market. By contrast, the markets in PJM and New England have both energy market and capacity market. The goal of an energy market is to match the generation supply and demand in the system on day-ahead and real-time basis and determine the market prices. In this sense, all energy markets in the country are similar. So the majority or all of the generators in the energy-only market, such as ERCOT, have to rely heavily on the revenue expected from the energy market. Now, once in a while, the generation supply can be tight. it can be short for various reasons. In this case, by market economic theory, the value of the supply will go up. So to reward those resources in this kind of scarcity situation, energy-only markets such as ALCA came up with a kind of scarcity pricing plan, which essentially raises the ceiling for the energy price. They call it the system-wide price cap. Over a number of years, Texas PUC has allowed to increase the price cap. And as of now, that system-wide price cap is $9,000 per megawatt hour, the highest in the nation. That is one of the key characteristics of the energy-only market. So I'm not surprised to see if you live in ALCA area and see your energy price goes up to $9,000 per megawatt hour if the supply is short. This is how the energy market in Texas was designed. Now, by contrast, big contrast, the electricity markets in the Eastern Interconnection, such as PJM, Mid-Continent ISO, for example, have some kind of capacity market mechanism to compensate for what is called a missing money problem. So basically, the missing money problem means that the revenue that some peaking generators earn in the energy market is not enough to cover the fixed cost of the generator. If a generator cannot recover its fixed cost from any available market, it will not survive economically. The electricity markets in the Eastern Interconnection chose an energy market with some kind of capacity market model because they believe that raising the energy price to a very high value is not politically sustainable. So in those markets, consumers pay extra money, call it premium, like an insurance, to make sure that there is a sufficient amount of generators available in case the system needs them in supply shortage situation like summer peak or even winter peak. I would say that although that kind of market design is not perfect, the consumers in these markets do not see the price shock. The cap they put in those markets is called a bid cap instead of price cap. So bid cap means the maximum bid that each generator can bid in an energy market, but the actual price can go slightly higher. That bid cap in PJM market used to be $1,000 per megawatt hour before the polar vortex in 2014 and 15. Then they raised that to the $2,000 per megawatt hour if the situation requires. During these polar vortex, PJM also experienced significant amount of generation outages. This will be the high-level view of the Texas power grids and its electricity market compared with the other grids and markets. Let me stop here and back to Jen.
Thank you for that overview. It actually really helps. One quick question, Jeremy. In terms of ERCOT, what would be the percentage of electricity breakdown that's coming from renewables, coal, natural gas, or nuclear that we might kind of expect on an average day?
Yeah, so based on the 2020 statistics, natural gas-fired generators provided about 40% of their total generation. Coal-fired generators provided about 18% of their total generation. Nuclear about 11%, and wind about 23%. And the rest of the generation came from other types of generators like solar, other types of generators.
Now, Alex, can you walk us through the sequence or the timeline of events that happened when the cold weather started to approach the region in mid-February and sort of what happened?
Yeah, of course. So when we actually start looking at the timeline of events, things actually start a little bit sooner. So every single season, ERCOT does what's called a seasonal assessment of resource adequacy. What it does is it looks at what resources does it have available, what power plants does it have, what power plants can it call upon, and what is the expected demand for that season. So ERCOT published its final seasonal assessment of resource adequacy for this winter in early November. And in that assessment, they have several key numbers that are worth noting. They had an estimate for forced outage rates in terms of how many plants are expected to be forced offline in severe scenarios. They had a planned outage rate, units that are not available because they're conducting normal operations and maintenance of their facility. And most importantly, they have an estimated demand level. And their estimated demand level has multiple components. They have a normal weather scenario, and then they have an extreme weather scenario. Their extreme weather scenario estimate, and this was what they thought was essentially the most severe weather they could face and that the grid would need to handle, was about 67 gigawatts. A gigawatt is a lot of power. It's about the size of one large nuclear plant or a very large coal plant. And so 67 gigawatts is around the maximum capacity that Texas has ever needed to serve in summer or in winter. Now, fast forward and we get to really first signs would be in late January, but early February. The first sign that something might be up is a weather forecast. Now, because of how weather forecasting works, we only have a certain level of certainty in terms of what it means for energy demand. About 14 days out is when we start entering a moderate level of certainty window. At that point, you can start estimating whether we're going to have somewhat colder, somewhat hotter, with relatively large error bars. By 7 days, the resolution gets much finer, and by about 5 days out, there's a very high level of certainty that we will be able to estimate what the weather conditions will be like. So things, as if you're looking in retrospect, about a week before the weather hit, ERCOT and the grid operator, as well as power plants individually, would have started to suspect that there might be an issue, that there would be an extreme demand scenario. Now, the market participants are going to be watching this very closely, particularly the seasonal assessment of resource adequacy for its estimated numbers, but also these weather forecasts, because this is where the scarcity pricing can happen, and this is where they can make their most money. And so if they know 5 or 6 days ahead of time, they'd want their plant to be online so that they can make money. The first sign that something was going wrong was Friday afternoon. Friday afternoon, gas prices, natural gas prices, started closing, and everyone started realizing in the market that there was massive demand for natural gas. Now, one thing that was unique about this storm, and is something that is a growing concern when we look at region-wide grid operations as well as energy systems operations, is this was a very wide-ranging event. It spanned most of the middle half of the country, from the Canadian border all the way down to Mexico. By the time that the event began, all of Texas was under a winter storm warning. And so this was a very severe demand scenario. And so the natural gas system was exceptionally stressed. There was a lot of demand both across the country and in the region. And so gas prices actually closed anywhere from 10 to 50 times more than they normally would be. And what that is a sign of is that there's very high demand for natural gas for industrial and commercial and residential heating, as well as for the power sector. And my concern, as soon as I saw that, I thought there would be rolling blackouts. This is something that has been a major concern for a while. And we have seen this historically with some other regions in the country, that we have this gas supply issue, that if there starts becoming a constraint in the gas supply system, power plants are the first ones to go out. Now, ERCOT in Texas began to respond. I believe the governor issued a natural disaster declaration on Friday. But one of the things that was striking about the beginning of this event is that the stringency of what was about to happen was not obvious to the public. If you compare this to the relatively minor blackouts that happened in California last summer, the grid operator there, CAISO, as well as the rest of the state, was very forward with people from the beginning. Whereas ERCOT, the level of communication they had, particularly at the beginning of the event, was very minimal. Most people were not aware that they were about to enter into tight grid conditions. The next step after the gas price day closed on Friday was that on Saturday and Sunday, we started having forecasts for Monday in terms of electric demand. And this is where I think alarm bells really started ringing. So remember that 67 gigawatt number that I mentioned earlier? Their estimated demand for Monday at peak demand was 74 or 75 gigawatts. Because Texas is historically not a winter peaking region, they use primarily electric for heating, and most houses are not insulated. And so if you were to do a curve of the relationship between temperature and demand, it slopes up much more quickly in Texas than other states. And because this scenario is so severe, they're estimating that the demand was 10 to 15% more intense or worse than their worst case planning scenario. That was not a good sign, and that was a sign that they might have to institute rolling blackouts, which is how we do manage situations when there might be supply constraints. Things really came to a head, though, on Monday morning. We weren't quite there yet, but we were at very high demand. 74 gigawatts, as a note, would have been a record demand for Texas ever, including summer. By the evening of going into Sunday evening and into Monday morning, we started having another huge issue, and that was forced outages. Now, there was a moment that I think was really severe, and I think grid operators around the country, now that they know about it, it terrifies them. There was about 10 minutes where the entire Texas grid was on the verge of collapse. To run an electric grid, you need to have a certain frequency. You need to have about 60 hertz. You can only have minor deviations from that, or else it can cause grid damage. Because the forced outage rate was so high, because units that were expected to be there were not there, there started being a large deviation in the grid frequency. The hertz at the most severe point got down to 59.3. That might sound like that's not that big of a difference from 60, but that's a really big issue when you're talking about very expensive equipment. If power plants are connected to a grid that's operated at below about 59.5 hertz for a large period of time, they can suffer major physical damage. And so they can only do that for a few minutes before they're forced to exit the grid to protect their equipment. Texas was there for almost 10 minutes. If you look at when the event began, and what they had to do is they had to cut almost 7,000 megawatts of load, 7 gigawatts over the course of that 10 minutes, or else the entire grid would have collapsed. Because Texas does not have interconnections to the rest of the country, the entire system would have been out. We don't know how quickly they could have gotten it back online. It could still be offline because a lot of the units that we use to restore the grid in that scenario, what's called a black start scenario, were suffering forced outages. So we don't actually know if they would have been available to get the grid back online. So that's a really severe scenario. And that's something I want to emphasize, that as terrible as what happened was, it could have been much worse. And it could have been something similar to what happened to Puerto Rico with the hurricanes. So they were able to avoid that by shedding a lot of electric demand. But the problem was that the rate of forced outages was gigantic. It was much more than they expected. I think at the peak, something like almost half of total expected electric capacity in the state was not available. And that was due to a number of reasons. If you look at some of the resources, there was a lot of focus on wind because of ice turbines causing problems. That actually wasn't a big planning consideration. They expected wind not to produce too much during these type of events. There was a small issue at a nuclear unit that tripped it offline for about a day and a half, and that cut some of the nuclear generation. There were some issues at several coal facilities that cut their generation. But the big issue is that Texas was depending on natural gas to provide the majority of a capacity during an event like this. They were expecting 2/3 of their capacity to come from natural gas. At points, it got down to almost 50% of that capacity wasn't available. Why? A number of reasons. First, because of that really massive natural gas demand, because there were issues on the natural gas system. There were wells freezing, there were demand issues. There was actually the electricity blackout started impacting the natural gas ability to move through the system. You had a lack of natural gas availability. You also had plants that were not winterized, and so they suffered forced outages when they were not available. At its peak, the outages were about 20 gigawatts. That's about as much electricity as New England consumes on average. So New England's worth of electricity was gone, and it was almost gone for 4 days. And so that is a really severe event. The amount of people that lost power is probably close to 8 to 10 million for an extended period. These were not rolling outages. The grid was in such a fragile condition, they had to cut power to everything except for important parts of the grid, like hospitals, or else they would have lost the entire grid. And even then, there were a lot of issues at hospitals and other critical infrastructure, including some water infrastructure, which caused some of the resulting issues. So now that we've kind of gotten to this point where we have power back, this event's not over. We're going to have to pay the people of Texas, power companies in Texas, are going to be paying for this for decades. The total event probably cost $50 billion because of these scarcity price designs, as well as issues in the natural gas system. And so this is going to be a continuing economic burden on the state as it tries to figure out how to move on from what happened.
Thank you for that assessment. And it actually sounds worse than I thought it was. So in your analysis, would you say that the natural gas side of things was the biggest fail of the system? And that is that what you're saying? And is there any part of the system that was not affected by the cold weather, just out of curiosity?
So the highest level failure here was a failure of market design and grid planning. This was something that we could have figured out a way ahead of time to manage this event. By having Texas on a separate grid, you prevented the ability to import power from other areas. But the fact is, El Paso kept power. They're on a separate part of the grid. They're still in Texas. They kept power. We had very minor amount of outages in the adjacent ISOs because they're able to import power from adjacent electric grids. So at the highest level, this was a grid failure. That said, when we talk about reliability, we talk about what are called N+1 events, basically one incident away from losing reliability or having a reliability issue. The problems, because this country has gone so quickly to natural gas, and especially the Texas ERCOT, the Texas grid, California to a lesser degree, the natural gas system is an N+1 issue. If the natural gas system doesn't deliver, it poses a reliability threat to the whole system. In our grid planning and our general electricity planning does not really account for how do you manage that risk. Natural gas is assumed to always be there. It's supposed to be a firm dispatchable resource. It wasn't there. And the worst part is we know that happens. That's happened before in the US.
I was zoomed in a little too much. You're right. Okay, that makes more sense. Jeremy, so as we're breaking down what happened, we all tend to have kind of a hindsight is 2020, especially after a disaster has occurred. It's really easy to look back and say, well, we should have done this, and to deconstruct things and sometimes even point fingers. But can you explain to us for a moment, especially since we have probably a broad number of people in our audience that maybe aren't familiar with this term, but can you explain for a moment, what is grid planning and how grid planning did or did not work effectively in this situation? Alex, I think, mentioned it a bit, but can you also kind of address that as well?
Yeah, sure. So in grid planning, the grid planners are looking at the load forecast, generation expansion, equipment aging, the growth of demand response, and changes in the export-import, the neighboring system, policy drivers, etc. And the planners will look at the next 5 to 15 years out, make a lot of projections, forecasts, and to see if the current transmission grid can handle those changes, and to see if there will be bottlenecks, issues on both real and reactive power flow and voltage constraints, etc. So then they run their transmission analysis and other analysis and propose some transmission solutions to alleviate those potential issues. They will go through their planning process, including stakeholders process, approval by the board, in this case like ARCO board. Once these proposed upgrades are approved, the respective transmission owners will build, construct, and operate these upgrades. When the grid planners do these analyses, they make sure that the system or the grid can handle what is called the N-1 events. I'm glad that Alex touched on it. N here means the number of facilities in the grid, such as transmission lines, generators, other equipment, etc. So the current system in the country is well designed to handle losing one electrical equipment, such as one transmission line or one generator. That is not a problem. But beyond the N-1 is a little dicey. The grid planner also plans for what is called N-2, which means losing two equipment simultaneously, and also like N-1 minus 1. So losing one equipment now and losing another subsequent. But the system is not designed to handle the loss of multiple equipment, such as losing a number of generators at the same time. It's also called the common mode outages. So when it comes to the extreme weather events or some unusual events, whatever that may be, ARCO grid or any other grid was not designed to handle that type of situation, like losing multiple generators or losing multiple transmission lines or combination of those. If you recall the 2003 Northeast blackout, it started with losing a couple of lines and generators, and it cascaded to the losing the entire grid in Ohio and New York. We call it cascading failure. And it is a topic related to the system resilience, which means the system can withstand and recover from those cascading failure events without losing too much power. So back to Jen.
Thank you for explaining that. So there has been some debate as to whether or not these extreme cold weather events, especially in lower latitudes, will become more common with climate change. And Governor Greg Abbott for the state of Texas said last week that he would mandate and fund the winterization of power infrastructure. And Alex, you mentioned winterization of the grid a second ago. So my question is for you, Alex. What does winterization of the Texas grid involve? For comparison, are the eastern and western power grids appropriately winterized for the kind of storms that we actually saw in February that hit Texas too?
Yeah, so that's a great question. I think that that is a focus of a lot of the technical solutions to try and move on from what happened. So when you're looking at designing a power plant, you face a number of design choices and engineering constraints and trade-offs. And so when you are looking at how to best make money in the electric grid or to serve any sort of needs, You're going to design that plant for the prevailing weather conditions, as well as the potential capacity or other sort of reliability requirements. So when you're looking at Texas, Texas is historically a summer peaking grid. They have had some winter storms like this, which is a big issue that they have had after action reports that found very similar things happened and there was not action taken. So this was potentially preventable if that had been addressed, if those winterization recommendations had previously been taken up. But essentially, the power plants are not necessarily designed to operate in sub-zero temperatures. That compares differently to, say, a place like PJM or MISO, which is the middle part of the country, or New York or New England, where winter is one of the major planning constraints for the grid. And so even the way that the power plants are designed is to actually handle those weather conditions. One common thing in a place like Texas is a lot of power plants don't have walls. It might seem kind of crazy, but what they're trying to do is they're trying to increase the ability of the power plant to cool in very hot conditions. It's because you really want to have the maximum production when it's hot out. And so not having walls, not needing to cool the reactor building or the turbine building can really help your plant efficiency. The problem is that, and then in winter conditions, that exposes your plant to the elements. There's other things. So the nuclear unit that tripped, the nuclear unit had a sensor issue that led to essentially a perception that there was a feed water issue to the plant. And so they went ahead and scrammed the plant and they had to take a little bit of time to restart it. That was a relatively minor issue, and they're going to be looking at why that happened. There are things like that are small sensor things that are they seem relatively small, but if you haven't been preparing for them, if you're not ready for them, your plant's not going to be ready for them. Comparably, the nuclear fleet across the country actually did very well with this overall event. This was something that was stressing multiple grids, and most nuclear units around the country were online. They were not suffering forced outages. So there are operational lessons, but there's also potentially some things that some individual operators might have done that was maybe not what we do in a northern latitude. So looking forward, it's going to be a question of, can we pay for winterization? I know the governor has said that. I'm not sure I believe that. Texas has decided previously not to do these type of winterization actions. And one of the big issues here is that you're not just talking about the electric grid, you're also talking about the natural gas grid. For the same reasons for electricity infrastructure that's just not designed for that type of weather event, the natural gas grid also had issues that related to the weather. And so you actually have to do overall energy systems hardening. But that has a cost. And if it's something that's only going to pay for itself once every 10 or 15 or 20 years, that's difficult to do. And one of the issues with the Texas market is there's not necessarily an incentive for you to make that investment. There's the hope that the scarcity price will create some sort of incentive so that after this event, if your plant was offline, you could say, oh, well, when this happens again in 10 years, I can make a lot of money. So I need to make sure my plant is winterized and ready every single year for this event. That's a big financial burden potentially. And that's a lot of money that you could be putting elsewhere. And so it's not clear you're going to have that with market incentives alone. So we need to figure out either by reliability centers at a national level or by other sort of state policy, can we encourage grid operators to make those investments?
Well, I have another question to kind of build on that. So, because we've kind of been focusing on winterization, but with climate change, from a weatherization and sort of being proactive in terms of climate change, we've been hearing and focusing on extreme cold, but is extreme cold weather more of a threat to grid resiliency than extreme hot weather? Which one, especially in a place like Texas, or maybe even in a place like here in Maryland or Virginia or the DC region, which one is a bigger threat in terms of grid resiliency, or are both? So I guess I'd like your thoughts on that.
Yeah, so that is a really good question. In the light of climate change, it's hard to make any sort of specific regional predictions. It's unclear whether there's a climate signal in the polar vortex, which is what ultimately caused this issue in Texas. It's what caused a similar issue that didn't cause blackouts in PJM in 2014. We're not sure if there's a climate signal there, but just generally looking at what climate does, we do expect more extreme weather scenarios. And what I would actually say is I think that this should be a wake-up call that historically we plan the electric grid on meeting peak summer demand because of air conditioning demand. That's when we have to do most of it. And because of climate change, the air conditioning demand is going to increase. It's going to potentially have reliability implications. But because of solar power, because solar power is so cheap, because solar power and batteries can help us get that main peak down, we actually might not have the same reliability concerns, at least to the degree that we used to, about summer peaking. It might become a summer peaking and a winter peaking concern. And the issue with winter peaking is because we've done this gas electric integration, it's not the maximum amount of electricity demand per se, but is the maximum amount of energy demand, the amount of demand that we have in the form of natural gas to provide heating for houses, especially for New England, New York, places like Washington, DC. The amount of demand that's happening overall on an overall energy basis is at its maximum in the winter when you include electricity and the natural gas system. And so over time, especially as we go towards renewable resources that may not perform as well in winter conditions, we need to figure out how to maintain that reliability and decarbonize the whole system. And I think that decarbonizing winter peak demand is going to be much more difficult than electricity summer demand.
And that also kind of reminds me of a different question that I have, and this can be for either one of you. We've been talking a bit about natural gas today. Is natural gas still the best dispatchable resource in our sort of future climate change world? Or do you see something else on the horizon that will also start to fill that void, just out of curiosity?
Should I jump in? Yeah. So as of now, there's so much technological advancement in natural gas, not just big combined cycle units, but the smaller modular, so you can put any place you like. It doesn't take a lot of space, and definitely dispatchable, controllable, and every system operator likes this kind of resources. But I don't say this will be the only the player in town, because with the growing the growth of the storage resources, and people are starting to see a lot of values in terms of like not just putting the storage any way you like, but if you combine with like wind and combine with the solar, and then that will create a very attractive sort of type of resources where you actually increase your controllability and dispatchability of resources. And I can see those type of resources will be coming into the system in a mass number in the future.
And on natural gas specifically, one thing I think is really unappreciated about what happened with the coal to gas transition, that was turbocharged when the shale revolution happened because of past infrastructure decisions. We had an existing natural gas grid that was largely empty for most of the year because it was built to meet this winter demand. And we also built a large amount of natural gas combined cycle units between 2000 and 2005. In fact, most of the fleet came from a big boom then. And so we've been growing the rest of the natural gas system since the shale revolution began, but we basically had a lot of slack, and we took advantage of that slack. And now what we're seeing is it's a systematic issue. So when we're talking about resources, nuclear units, to a degree coal units, renewable units are kind of unique because they're a self-contained operational system. A natural gas system that does not have on-site storage is part of a natural gas plant does not have on-site storage, is part of a natural gas system. And so we need to think about that from a systems management level. And that's something where the dispatchability might not be what we thought anymore. It's not just something that's an inherent trait of natural gas. It's an emergent characteristic from the natural gas system.
Thank you for explaining that. But my question is for both of you, and you guys can choose to answer them in any order. As we wrap things up and we look to the future and try to learn from these heartbreaking and painful experiences that have played out in Texas over the last 2 weeks, what changes do you anticipate will occur in Texas in response to what happened from a policy and a regulatory perspective? And either of you can take this first.
Yeah, let me jump in first.
Sure.
So the easy one is, Alex mentioned that weatherization. I think there will be no more excuses. So the wind turbines in Texas should be equally weatherized as those in Oklahoma or North Dakota. If the wind turbines in Oklahoma can withstand extreme cold, why not the ones in Texas? So same for the other types of generators. The second is a big one, is the interconnection with the neighboring system. Interconnection brings two benefits: economics and reliability. I'm not going to say one way or the other because Texans are very proud of their independence. That topic of interconnection should be revisited and thoroughly studied before making a decision. I would personally favor the interconnection because there are many benefits associated with the interconnection with the neighboring system. It is not a panacea for this type of problem, but it will be one of the changes that can alleviate this kind of impact from this kind of event. I want to give one good example. When ARCA started, the electric utilities in Texas were interconnected. Why they were interconnected? Because they saw the benefits of interconnection. Now, if they extend that idea to the neighboring system, voila. So benefits will expand, and if you're short, I will help, and if I'm short, you will help, right? So in terms of the capacity market, I'm a little reluctant to advocate for this because Texans are, again, very proud of the energy-only market. We had the debate for a long time in power industry when ARCA decided to continue the part of energy-only market. If the high price ceiling, such as $9,000 per megawatt hour, is sustainable, they can continue with the energy-only market. If it is not, they have to consider at least some kind of payment mechanism for the generators to make sure that they're available during the supply shortage. But it's up to the policymakers to decide whether and how they want to go with this type of compensation mechanism. The last point would be the reserve margin mandate. Reserve margin means the extra amount of capacity available above the projected peak load. Could be a winter, could be a summer. Markets like PJM, MISO, New York all have that. So I'm a little surprised to know that ARCA doesn't have the mandate. I think that will be coming sooner or later. Back to Jen.
So I'm going to maybe be a little more cynical, and I'm going to say nothing's going to happen. And I do hate to say that, but look, the thing is, this happened in early February. It's early March now. The Texas legislature will be done meeting in about 2 months. So if they need to do something, they need to do something fast because they do not meet next year. The Texas legislature only meets every other year. And for there to be a legislative push, it's going to happen very quickly because it's not going to happen in 2 years. There's not going to be the same type of urgency. And so because of the things that Jeremy mentioned, that Texas is really proud of its energy only market. It does not want to be connected to the rest of the US electricity system, and it does not want federal regulation. They are going to be resistant to a lot of changes. And part of the thing that I think is really challenging when you're looking at what can they do moving forward, they have a $50 billion or so energy bill that they need to figure out how to allocate and how to determine how to pay for, and that's going to go on consumers. And so these things cost money, and so putting that on top of that bill they're already paying, that's going to be a political challenge. Now, there are things that I think you could change, and I do hope that there might be some things that we can actually do at the national level. I think NERC in particular, which oversees North American electricity reliability, should look very seriously at winterization and weatherization standards. I believe that they've already started doing so. But the thing that does concern me about this is something that's been happening for several grids in winter seasons for the last 10 years. There was a similar incident several years ago in the South Central United States. PJM faced a similar issue in 2014, which I think they've done a good job on the market side in trying to prevent moving forward with how their capacity market works. But there are things here at the plant level that I think we could really have a better conversation about how to regulate. And so if there are changes, I think it might come from outside of Texas. And I think this event might be more impactful for how other grids operate and how they deal with these type of issues than necessarily ERCOT itself.
Thank you, both of you, for your assessment. We'll start going to questions now from the chat. Our first question is coming from Sarah. Sarah would like to know, will fuel costs in other utilities outside of Texas also increase in the short term as a result of the scarcity that occurred in Texas? And are those likely to be pushed on to consumers? I think she means it presumably, or customers in those regions. Who would like to answer that, Jeremy or Alex?
Yeah, I can take that. Outside of Texas, it's harder to say. So when you start getting into kind of market level analysis, there's a lot of weird interconnections that kind of happen across all these systems. So a lot of the scarcity pricing and severe gas price effects will be located primarily in Texas, but there could be knock-on effects. There were other scarcity issues in nearby electric grids that I think will have their own issues. But potentially, depending on whether this causes any sort of additional investment in the gas pipeline network, whether there's any sort of requirements for additional weatherization at any sort of the gas infrastructure, or to a lesser degree, if you have any sort of things that are required of a company that operates in Texas and they have multi-jurisdictional operations, there could be knock-on effects. It gets really complicated, and I don't think it's going to be that much compared to what's happened in Texas.
Okay, thank you. We have another question coming from Chris. Actually, two questions. The first one is there any indication so far that generators or fuel suppliers gamed the system in Texas to curtail supply in order to boost profits? 2 decades ago, Enron did something similar. His second question is, does the experience in ERCOT territory with so-called firm generation being unavailable cause the ISOs elsewhere to reevaluate capacity market design and capacity payments? If thermal plants are less reliable than previously understood, then will other ISOs change their evaluations and plans?
Well, let me jump on this. So I want to give an analogy that PJM experienced, the polar vortex back in 2014 and 15. Again, I mentioned about common mode outages when, the gas supply is short or, disrupted. The gas-fired generators also lose the gas, and then they cannot produce the energy. I don't think the generators, the gas-fired generators, game the system. They definitely would like to produce energy. That's how they will make money. I think the similar events happened in Texas energy crisis because of that deep freeze, and it frees up, disrupted their gas supply, causing the disruption in the gas supply to the gas-fired generators. And there's no gas and they have no electricity. Yeah.
Just quickly, I think that's all right. On the gaming question in particular, one thing that is unique about this event is how severe it was. There was 20 megawatts of unmet demand at some point. No one in Texas has that much market power, and prices are already at $9,000. And so if you had anything you'd want to run at that point, market power in these type of electric systems really happens when the imbalance between supply and demand is relatively small, and you can influence that with a generator. And we have systems and techniques to be able to try and detect that. In this case, the prices hit $9,000 and they were there for days because there just wasn't any sort of electricity available. And there really wouldn't be any incentives to game the system there. The incentives in that situation are to run your plant if you possibly can.
Thank you. Thank you for going through that. We also had another question from Skylar, which I didn't ask earlier, so I apologize, Skylar. Skylar asked, what was the total percentage change, if you guys know this, from before the storm to the middle of the storm with respect to increase of demand? And what caused the shortage of natural gas exactly?
So the numbers, this is ballparking, but I believe it's about a 40 to 50% increase between demand before the storm and projected peak demand. So that's a pretty significant increase. And then during the storm itself, the actual capacity delivered was around 50,000. So compared to before the storm, it really wasn't that much of an increase. It really was on net demand. In terms of the natural gas shortages, we're still trying to understand that. It's going to be a while until they can do the post-event analysis. But I think there are two buckets that things will fall into: gas supply issues and plant-level natural gas issues. And so gas supply issues are things like wells freezing off, oil and natural gas production in the state and actually the region collapsed. We actually saw a very large collapse in oil production, which we haven't seen in a long time. So at the well, we just weren't producing. There are physical limits to how much you can get out of storage, especially in a place like Texas, which isn't really designed to have a lot go out of storage at once for these type of events. And then there were also issues in delivering the gas, especially once you start having the power outages, because these systems are interlinked. And so there were gas compressor stations that couldn't get power to keep sending natural gas. So those were the system level issues. At the plant level issues, it's usually going to be some sort of issue with the plant not being weatherized, or potentially some sort of pressure issue that you cannot actually get pressure at that specific plant because of the upstream pipeline issues.
Thank you. We had another question from Raul. Besides interconnection, gas, and nuclear, what each community on an individual, I think he's asking, what can an individual in a community should do to prepare for this type of event? Focusing on the individual level and the community level. Any recommendations from either of you?
Yeah, let me jump in here. So I mean, Texas, most of the time, a lot of, you're exposed to a lot of sun. So you can put a rooftop solar yourself. And I have a colleague in Austin, and he's always shared with me how proud he is having an electric vehicle, little storage, and then some, solar power, the rooftop. So he actually self-sufficient, and he kept saying, "I don't need the power from the Austin Energy." So that's one way you can do. You can do like community solar. I mean, of course, in wintertime, you're not going to get a lot of solar energy, but it's a way to sort of become self-sufficient, and then you can even sell the power to the grid.
In terms of community preparedness, I think that's a really good question. We kind of talked about this like this was a man-made disaster. It was a man-made disaster, but the proximate cause was the natural disaster. This was really severe weather. And if we're looking at what projections are saying for climate change, communities in general need to be more resilient. They need to be more prepared. So the degree that you can do simple things like just having a go bag or something like that in case you need to evacuate a region if you're in a hurricane area or something similar. Making sure that you have bottled water in the house in case for some reason you lose water like what happened here. Having plans in case you do have some sort of power outage like this so that you have a place to go, or even just being aware of what those resources are and knowing who to listen to when you have one of these type of events. This falls into, I think, a broader bucket of what is community preparedness for natural disasters? What does that look like, and what role can you play? And especially if you can, especially if you can afford it, have extra stuff so that you can help out your community if they need it. If you could have like a couple extra dozen bottles of water right now, that would have really helped some people in the height of this crisis.
I like your recommendation for having a go bag. That's something that a lot of people I know that live on the West Coast tend to have for wildfires. One thing we do in hurricane prone areas is whenever one is coming and we know we're going to lose power, we tend to fill up all of our bathtubs because we know that when we lose power, we're not going to have any water. But thank you for both of those recommendations. So I want to thank everyone for joining us today, and I want to thank our panelists. One thing I also want to remind everyone that, again, there's still a lot of people in Texas, but also in other regions not in Texas that are also affected by this severe weather event and power outages. So it's not just people in Texas. We just focused on Texas as a case study. So I encourage you guys in your sense of charity to reach out to, we picked food banks because a lot of people lost a lot of food, but there's other ways that you can help people in these regions. A lot of people suffered a lot of property damage and people need help. So I encourage you to help in ways that you can. I recommend, if you can, helping at a local food bank like North Texas Food Bank, Central Texas Food Bank, or Houston Food Bank, but there are other ways that you can help in those local communities, and I encourage you to do so. But thank you so much for joining us today. So thank you for joining us, and we really appreciate your questions. Thank you very much.
Thank you.
Jen.